estimate the data. So, in section 12.1, we're going to talk about the inference for linear regression. So it's kind of like what we did before with proportions and means, but now we're going to be doing the inference for the slope of our regression line. So what do we expect the slope? Is there an actual linear relationship between two variables? So the example that they use in the book, they look at the relationship between a person's percent body fat and their waist size. So they want to see if there's some sort of relationship between those two variables. So they collected a sample of individuals. They measured their waist size, they measured their percent body fat, and they create the following scatter plot. So we have waist size as our explanatory variable. We have percent body fat as our response variable. So those are some things that you might want to go back and review, some of the terminology. So explanatory always goes for X, response always goes for Y. So each of these people, they recorded the two pieces of information and plotted them like an XY. Okay. So based on our sample, does it appear that there's a linear relationship between waist size and percent body fat? Yes. Now, the question here, though, is this is from one sample. Can we determine then that if I were to take sample after sample after sample, that we'd always find a linear relationship between waist size and percent body fat? That's what we're trying to determine. So is this enough evidence to suggest that we do in fact have some sort of relationship? Or was this just kind of a weird sample and there's really not a linear relationship between the two? So that's kind of what we're looking at overall here. Now, when we look at this, a couple of things to kind of go back and remember. So you don't have to write any of this stuff down since it should be reviewed. Now, if it's something you want to, you can. But when we talk about regression, we're modeling the relationship between two quantitative variables. So we're taking the actual data, that scatter plot, so those points that are scattered all over the graph there, and we're going to fit a line to it. That was our line of best fit. So that line is going to estimate values of y based on values of x. So it's not going to give us exact values from the data, but it's going to give us estimated values. We're modeling that relationship. Okay? So we used that regression model when we created our line to predict values based on the model created. So whatever our line said, we plugged x in for that, we were able to get our y value out. So that was a predicted value. Now we want to expand. So that would tell us for just this one sample. If I plug in a certain waist size, I could get a predicted percent body fat for the people within my group. So for the people that I actually collected information from. But we want to know if we can go outside the scope of these individuals. What does it tell us about the general population overall? So that's kind of what we're going for here. So when we tested means and proportions, we could imagine one true underlying value for the parameter. So when we tested, we started off with an assumption. We believe the correct mean is this. And then we ran a hypothesis test to determine if that mean was correct or not. Or we had proportions. We believe the true population proportion is this. We run a test to determine if it is or not. And we had the option, we could say greater than, less than, not equal to. So that's kind of what we were dealing with there. The same kind of idea is going to happen with slope. So how do we work this with regression? Well, we know better than to think that if I found every single person's information, so if I was able to go out to the entire population, measure every single person's waist size, and get their percent body fat, that my data would line up in a straight line. Real world data just doesn't do that. So when we're looking at this, the whole idea is determining whether we have that linear relationship or not based on the sample we're looking at. Now, what happens here is that for the individuals with a 38-inch waist, so for individuals who have a 38-inch waist, there's an entire distribution of percent body fats just for that one waist size. So if we looked at only the people with 38-inch waists, we have all kinds of different percent body fats that come along with it. So we have an entire distribution that goes with that one waist size. And so that means for every waist size we measure, 36, 37, 39, whatever, right? Each of those waist sizes is going to have its own distribution. So what's actually happening here, when we look at our regression model, so if we had certain waist sizes along the bottom, so like let's say we had 34, 35, 36, 37, 38, okay? At 34 inches has an entire distribution of percent body fat. If we only look at those values, we could create a histogram to show the distribution of percent body fat for 34-inch waists. If we went to 35-inch waist, we have an entire distribution of percent body fats for that particular waist size, and so on. Now, when we create our regression model, that line that we create obviously can't hit every single point within that particular distribution. But what do you suppose it should hit? The mean. So when we create our regression model, that model assumes that the means of each of those distributions falls directly on the line, even though individuals scatter around it. So if we matched up all of our distributions, if we lined them up along this y-axis here and put them out in order, we should be able to draw a straight line through the means of each of those distributions. So if we plotted each of those means, we should have a straight line all the way through. That's what our model is telling us should happen. Is everyone okay with that idea? So when we're doing our model, we're not trying to catch every single point because it's not possible. But what should be happening is we should be capturing the mean of every distribution we have for each individual waist size. Or, within your given scenario, whatever your explanatory variable is. So, here's where you probably want to start kind of writing stuff down. This is the stuff that's going to pertain mostly to what we're doing here. So when we write our regression line, now before we wrote our regression line using this notation. So y hat was a predicted value of y. So this is not an actual value of y from the data. It was predicted based on the model. So we had y hat was equal to a, which was the y-intercept. B was the slope of the line, and then x was the value for x in our particular scenario. So if we wanted to predict for y, we would take a certain waist size, plug it in for x, use our slope and y-intercept to calculate that predicted value. Now, since we're talking inference, so now we're trying to go beyond the scope of one single sample. We want to see from this sample, what can we say about the general population? So we're going for parameter values. And parameters are always notated in Greek letters. So instead of A and B, we're going to use alpha and beta. So alpha is going to be our intercept, beta is going to be our slope. The other thing that's going to happen here is instead of y hat, we're talking about the mean of the y values. So at each level of x, our line should be giving us the mean of the y values. So remember, each value of x had its own distribution. So if we take the mean of that distribution, the mean of the y values for that one distribution, that's what our line is going to give us. So mu sub y is equal to alpha plus beta x. Essentially the same as before, y equals a plus b. We're just using some different notation to denote that this is for a parameter. It's from the overall population. Everyone okay with that? Okay. So, in order to test, or in order to create a confidence interval, we're going to talk about both. In order to test the hypothesis, there are some assumptions and conditions we need to check. Now, these assumptions and conditions are a little more in-depth than the conditions and assumptions that we had before. So it's not just simply the random 10% large enough. Also, the order in which you check the conditions is important. You need to make sure you do it in a certain order so that if at any point you see something wrong, you can stop immediately and say we can't continue with what we got. But you have to check them in these orders to make sure you're doing everything correctly. So the first one is to check what's called the linear condition. So based on our sample of information, do we actually have a linear relationship for the sample? So to check for linearity, simply check your scatter plot. So you take the information given in the problem, make a scatter plot, and check for linearity. Okay. After we've checked the linear conditions, so now that we know we actually have some sort of linear relationship, we can continue on to the next, which would be the independent condition. So you need to be able to justify or explain that the individuals in the study are independent of each other. So each of the individuals should be independent from one another. They shouldn't have any sort of relationship between them. Now the next two, randomization and equal standard deviation. Okay, so randomization and equal standard deviation. The randomization here doesn't mean we took a random sample from the population. It means that our values are randomly scattered around. So are the values actually randomly scattered along the residuals? The equal standard deviation says that for each value of x, so for each value of x, remember we have an entire distribution of y, correct? So for each value of x, is the standard deviation for y the same? So does there appear to be an even amount of scatter throughout the entire plot? So both of these conditions can be checked at the exact same time by looking at a residual plot. So you start with your scatter plot to make sure that it's linear to begin with. Check your independence conditions, so just verify that the individuals were independent of each other. And then your next two conditions can actually be checked using a residual plot. So then you go into your scatter plot, instead of using list 2 for y, you would use your residual line for y. And you're looking for random scatter, so you don't want to see any sort of pattern within the residuals. You don't want to see a curve or anything like that. And for equal standard deviation, then you're looking, as you progress from left to right, does the spread of the dots appear to be equally distributed? So for instance, if you were looking at a residual plot, and you saw something like this, what condition would we be failing? The equal standard deviation. As x is getting larger and larger, the distribution along y is getting smaller and smaller, right? So I don't have an equal standard deviation. If I looked at my standard deviation for y at this x value, it's going to be much larger than the standard deviation of y at this x value. And we need it to be fairly similar all the way throughout.
How do you get the residual, like, on your calculator?
So on your calculators, if you want the residual, so remember your scatter plot is located in that second y equals. So you go to your stat plot. So go ahead and choose plot 1. And so what you would do here is you would choose, so make sure plot 1 gets turned on, so you'd have to have the on button hit enter to make sure it's highlighted. If you're going to do a scatter plot, so a residual plot is just a scatter plot with just some different inputs. So what you're going to do is you're going to choose the scatter plot, that's the very first graph. And then when it asks for your x list and y list, So X list is just going to be list 1. Where did you put your explanatory variable? So that should always be list 1. Y list, by default, should say list 2 right now, correct? For most of you, so list 1, list 2 should be in there right now. Now, that will get you your normal scatter plot. So that gets you your first condition. Okay? When you want to go to residuals, though, you have to change that Y list. So you're going to go down and highlight that Y list. So it shouldn't be list, or you should be highlighting list 2 right now. And then if you hit second stat, when you scroll down to the bottom, it should be one of the bottom values. It should say something that says resid. You want to choose that option. So you want to choose that option that says resid in that second stat menu. Now, be aware that in order for it to calculate residuals, you will have had to put in your regression line into your calculator. So you would actually have to use list 1, list 2. You'd have to run your linreg ax plus b function. So let's review that. If we have our 2 lists entered, we'd have to actually run the linreg function so that your calculator has a line to work with. So you find that by going into stat, over to calculate, and then it should be like option 4 for most of you, linreg ax plus b, or you can go to option 8, linreg a plus bx. So you'd actually have to run that function, so you hit enter, it comes up on the screen, hit enter again to run it. Then once your calculator has a line stored in it, now you can run your scatter plot with the residuals and it'll know what to do. Okay, so if you run a residual plot and you get an error message, it means that you haven't run your linreg function yet.
What's free list and store?
Nothing, just leave those alone.
Blank.
Yep, so you'd always just do list 1, list 2, leave everything else the same, and
So we don't change list wide, or is it, that's just for the scatter plot?
that's just for the plot. So on that, when you're running the, when you want to actually calculate the line, you just use list 1, list 2 always. You'll never change those. Okay? So only in stat plot, only in the graphing part will you ever change to residual, and that's for these 2 conditions. We're okay with that? Okay? And then the last condition, is the normal condition. So we need to make sure that our residuals are normally distributed. So the easiest way to determine that, anytime you want to use your calculator for normality, the normal probability plot is usually the easiest one to work. So let's review that process. If you want a normal probability plot, you go into your second y equals, so get into your stat plot. So choose your plot. Usually plot 1 is the one you'd want to use by default. Now instead of choosing the regular scatter plot, because we don't want that anymore, we're done with that, you want to go to the very last option. So the very last option for graphs, and select that option. Make sure you actually hit enter on it so it changes to that option. And now it should only ask for one single list, right? So it asks for one single list, which in your case would be the residual list. So we want to know how the MPP looks for the residuals. So you'd highlight whatever list is there. Usually it's list 1 by default. So highlight whatever list is there, hit your second stat, and then scroll down to the resid option. So you want to make sure you do the MPP for residuals. And when you look at your normal probability plot, how do you determine if it's normal or not? So if you actually had data in your calculator and you ran a normal probability plot, what should the graph look like for it to be normal? It should be linear. Okay, so it should be linear overall. If it's got any sort of big curve to it, that means your residuals are not normally distributed, which means you wouldn't be able to proceed with the process that we're going to discuss here. Okay with that? So, lots of conditions to keep track of. Basically, you make a scatter plot of your data, check to make sure it's linear, mention something about individuals being independent of one another, check your residual plot, that gives you your next two, so the randomization and equal standard deviation, and then create a normal probability plot for your residuals to check your last normal condition. Okay there? All right, now, anytime we work with hypothesis tests, anytime we work with confidence intervals, one of the things that we have to discuss is standard error. So everything we've used so far as inference for means, proportions, with our chi-square, we always had a standard error that we had to work with. So with regression inference, 3 different aspects will affect the standard error of our slope. So there's the standard deviation for the residuals. So the spread around the line. So this SE is the residual standard deviation. So if we looked at the distribution of the residuals, what's the standard deviation for those residuals? There's the spread around our x values. So this Sx is the standard deviation of just my x list. So if I look at the standard deviation of just my x variable, that's that Sx. And then the sample size will also play a role in the standard error. So when you put it all together, this would be the formula to calculate standard error. Now, most of the time, if you're asked to calculate standard error, they will probably give you the pieces you need. All you need to know is how to plug them in. So you would not necessarily need to calculate SE on your own, calculate SX on your own, and the sample size would always be given to you in the problem. So most of the time they'll just give you the pieces, you just have to be able to put them in correctly. So you would take your residual standard deviation divided by your standard deviation for x times the square root of your sample size minus 1. So you need to know this formula. It's not one that shows up in the formula packet. So it's not one that you're going to be given on a test. You need to know it. Now the good news is most of the time when we're working with these regression inference problems, we're using a lot of times a computer output. So computer generated output that tells us everything we need for the test or for the interval and so on. So a lot of the times while we talk about how to get it by hand, how to get all this information, get based on the data, most of the time you will not have to go through all this. Most of the time you just have to be able to look at an output, figure out what you need, plug it in, and get your answer from there. Okay, so while it seems like some of these have a lot of work involved, you won't be doing a lot of that work most of the time. Okay, but definitely know this formula, know how to work it based on the information. So, next thing. If we're running a hypothesis test, every time we've run a hypothesis test, we've needed a T or a test statistic. Anytime we work with proportions, we worked with a normal distribution, so our test statistic was Z. So we would calculate a Z value, use it to find a proportion from the table or from the calculator, and that would give us our p-value. When we worked with means, means followed the t-distribution, so we'd have to calculate a t-score, and then use that t-score to calculate our p-value. Regression slopes. If you think about how we set up the problem, it was mu sub y, the mean of the y's. Since that's a mean problem, we have to go back to that t-distribution. Now the other thing to note here, since we are working with 2 variables at once, So initially when we did the t-distribution for the mean of a sample, there was only one variable in question. Now we have those two variables, we have to adjust our calculations for degrees of freedom. So when we use our t-distribution in this case, our degrees of freedom are calculated by taking sample size minus 2. So that is a change from what we used previously. Previously with means we used n minus 1. Now as far as the calculation is concerned for t, it is exactly the same as before. You take your sample value, so this would be our sample slope, minus our population slope, which is always our null hypothesis value. So we get a sample value from the problem. We'll have a null hypothesized value, which is our population slope. That's our assumed slope. And then we have our standard error, which we talked about the formula for on the last slide, but in most cases we'll have a computer output that'll tell us exactly that value. Okay. Now, the other thing about this formula that you might want to know about, when we look at a hypothesis test, okay, if we set up our hypotheses, so null and alternative, remember our null hypothesis is always the hypothesis of no change. Well, for regression, what that means is we start off assuming that there is no linear relationship involved. So our null hypothesis for regression is that there is not a linear relationship between the two variables. So what that means, when we set up our null hypothesis, if we have no linear relationship between the variables, our slope should be 0. It should be a completely random scatter with no direction to our line. So our null hypothesis is always going to be that beta equals 0. We're always starting off assuming there's not a relationship. We will only conclude that there's a relationship if we find enough evidence to reject that null. So, for this formula, what does that mean? Very good. What that means is we really can boil this formula down to just the sample slope from the problem divided by the standard error of the slope. Because our hypothesized value will always be that beta equals 0. No linear relationship between. Once we have our t value, so once we know that t is equal to whatever specified value there, what would we use on our calculator to get our p-value? Well, the inverse would get us our critical value for a confidence interval. We'll talk about that here in a second. But if I know my t-value right now and I want to calculate a p-value from it, I would use t-CDF. So you'd use that t-CDF function where you have a lower bound, an upper bound, degrees of freedom, and then you get your p-value from that. Okay? So that would be the process. So if you're running a test, once you checked your conditions, you would calculate t, plug t into your t-CDF function, find your p-value, and use your p-value to determine if you reject or fail to reject. Now, like I said, for these types of problems, there's a lot of work involved. We're going to talk here in a second about the computer output that you'll mostly get with these types of problems and show you kind of where the pieces are that you need and how you put them together. So, we just talked about on the last slide, our null hypothesis. So when we run a test, our null hypothesis is that we have a slope of 0. That slope of 0 is basically saying that there is no linear relationship between the variables. So it's just truly a random scatter of dots. There's no actual relationship, no linear relationship between the two. Okay? So when we test that, that means that we have a value, a beta value of 0. That's our null. Now, just like any other test, we can run our alternative as greater than, less than, or not equal to. So it depends on what kind of question we want to answer. If we think about our two variables, our null is that there's going to be that there's no linear relationship between them. But if we would suspect a positive association, if we expect to see a positive association between the two variables, then what should our alternative beta be? Beta greater than 0. If we expect a negative association, we would say beta would be less than 0. And if we don't have an idea of direction, we would go with beta not equal to 0. So we think there's a linear relationship between the variables, we just don't know if it's going to be positive or negative. So that would be a not equal to problem. So the alternative, the null and alternatives are exactly the same as before. Beta is 0 for null, beta is greater than, less than, or not equal to for alternative. And then we carry on like any other hypothesis test. Check our conditions, find T, use TCDF to find P, draw your conclusion. Okay? So, confidence intervals. Confidence intervals are even easier. Now you still have to check the same conditions, but the formula for confidence intervals is exactly the same as the confidence intervals we dealt with proportions and means. So we take our sample slope, that lowercase b, plus or minus our t star, that's our critical value, times the standard error for b. So this is exactly the same as what we had before. Sample value plus or minus critical value times standard error. So sample slope plus or minus t star times standard error. Now, here's what most of your problems are going to look like. So they're going to give you a scenario. They're going to run through and say, this is the scenario we're working with. The data was collected. It was put into a program like Minitab or some other statistical software. And here's the output. So most of your problems are going to come out looking something like this. Okay? So some pieces that you would need to be able to identify or recognize within this output. And they're all going to look very similar to this. So they're not going to change it up. Every statistical software pretty much has the same output. Okay, so it's always going to be in the same spot regardless of the software used. So the first thing, this S value that they give you. So they're going to tell you what the dependent variable is. They'll tell you like an R squared, so the correlation squared value. And then they'll give you an S value, so S alone. That's your residual standard deviation. So that's that S sub E, which we use to calculate standard error. So if they were to ask you to calculate standard error, the first thing you would need is your residual standard deviation, and that's located where they give you the S value. They also tell you how many degrees of freedom your test would have. So in this case, there were 13 individuals in the sample, which means 11 degrees of freedom for our overall problem. Now, the other part of this then tells you everything you need to know about your regression line. So when we look down here, it tells you the variable name. So variable, the constant. Well, in my regression line, what value is the constant that's not attached to x? There's a slope and there's a y-intercept, right? So the constant, this is the term not attached to x, this is your y-intercept. So when you look at the term, or when you look at this type of output, when you see the word constant, and they'll always use the term constant, that's your y-intercept. So everything in that row is your y-intercept information. So the coefficient, if I were to set up my equation, this is my y-intercept, 92.6852. If I was running a test on the y-intercept, which is not something we do hardly ever. We're always more interested in the slope. Is there a relationship of some kind? But if we were running a test, here's my standard error. So there's my standard error for my y-intercept. Here would be my t-value for my y-intercept. Here would be my p-value for my test. Okay? So everything that has to do with constant is your y-intercept information, which means the variable that they name, so in this case they were looking at calories, that's all of your information for slope. So constant leads you to a y-intercept, named variable leads you to slope. So that means my b value, the actual sample slope, is 2.213. So the coefficient tells you the actual value of your slope and your y-intercept. The standard error for my slope is given in the standard error column. So the standard error of my coefficient, 0.5980, that would be standard error for my slope. The t-ratio is just your test statistic. If you actually took b divided by SE of b, so if you actually use the formula for t, that's the value you would get. So they usually calculate that t-value for you. And then if we took this t-value and we plugged it into our calculator in tcdf, we would receive our p-value for the given information. Now generally, when they run these tests in their computer software, the p-value they report will be two-tailed. What does that mean? It's looking at both tails. So if you were running an alternative hypothesis of beta not equal to 0, then this is exactly the p-value you would want. But if you had restricted your alternative to simply greater than or simply less than, what would you have to do with this value here? Cut it in half. This tells you what's in both tails, but if you're looking at greater than or less than, you're only looking at one tail. So you have to cut it in half to get just the one tail that you're interested in. Is everyone okay with that? So as far as the output goes, this is the most important piece, being able to pick out each of the individual pieces. Okay? So if I wanted to create a confidence interval for a problem like this, well, my confidence interval is found by taking b plus or minus t star times SE. So all I'd have to do is come into my table here. Well, here's b, plug it in. SE is here, plug it in. The only thing I'd have to worry about is finding my critical value, which we do by using what? Either the table. So the table's a really easy one to look at because you know what your confidence level would be. You know how many degrees of freedom you would have, so you just look for those degrees of freedom, go over to the correct percentage, and there's your t-star. Or, because the table only has certain values for degrees of freedom, what's another way to get more accurate? Inverse t on the calculator. So if you have that inverse t function on your calculator, you can use that inverse t, plug in the corresponding area, find your t-star, and then plug that in and find your interval. Okay? So from the computer output, if that's what you're given, you don't even have to really run your test for anything, because it's actually telling you what your t-value is, and it's telling you your p-value straight out. If you're running a confidence interval, that requires a little bit more work. There you actually have to pick out a couple of the pieces, plug it in, and then just evaluate. Okay? But for the most part, shouldn't be too involved if you have that computer output. And most of your problems will give you this information. So let's just run through a quick example here.
You said that looking at greater than less than, only look at one cell compared to not.
You cut the p-value. So this p-value right here. So my constant, that's my y-intercept. This I usually don't pay any attention to. The only thing I would use here is the coefficient, maybe if they wanted me to write the line. So if I wanted the equation of my line, I need this for my y-intercept. Otherwise, this is useless to us. So we go to our variable, and that's all the information I need. So my p-value would be 0.000, but that's for both tails. So if I wanted just one tail, I would just cut that value in half, and that's going to be the value of one tail. Okay, so below is the Minitab output for a least squares regression analysis on data that came from dropping 70 paper helicopters from various heights and measuring the flight times. So basically, it took just paper helicopters, they dropped them from a certain height and looked at how long it took them to fall to the ground. Okay, so if we're looking here, constant would be my y-intercept, drop height would be my slope. So, if we were answering certain questions here, it says part A, give the standard error for the slope. And then interpret this value in context. So looking at that table there, what value would correspond to the standard error for my slope? Very good. So my standard error is this value right here, 0.000202. So in the standard error column, but I need to make sure I'm working with slope, which is the named variable. Okay? So that's the value. Now, it's important to understand what that value means, because some of the questions you're going to have to answer is, what does standard errors mean? So as far as interpreting goes, if we repeated the random assignment many times, so if we were to drop these helicopters over and over and over again from different heights, okay, so if we repeated this process over and over, the slope of our regression line would typically vary by about 0.0002 from the true regression line. So if we were able to actually calculate the true regression line and get a value for its slope, the slopes we would obtain from our samples should be within 0.0002 of that initial slope. So that's telling you that if you repeat the process over and over again, your sample slope should typically vary by about the value of your standard error from the slope of the true regression line. So it's important to make sure you understand how to interpret that. Finding the critical value. So finding the critical value for a 95% confidence interval for the slope of the true regression line. So if we wanted 95% confidence, we want the critical value, which means we want our t star. We would either go into our calculator and plug into inverse t. So first of all, since there were 70 paper airplanes, 70 minus 2 gives me 68 degrees of freedom. So in my calculator, I would take inverse t. Now notice, my first value is the area I'm concerned with. Remember, 95% is the middle of my distribution. So I need to add in an extra 2.5% for one of my tails. So when you're doing your inverse function, remember you're plugging in area, not confidence level. So 0.975, comma 68. If you were doing this on the table, you'd have to look up how many degrees of freedom. Whatever's lowest. So the next lowest below 68, because 68 is not going to show up on the table, so probably 60. So you would use T star of 60, and then you'd look for 95% on your confidence level and go from there. So if you're using the table, that's the process for that. Okay? So if I want to calculate my confidence interval, I plug into my formula. B is the coefficient of my slope, 0.0057. T star we just calculated with 1.995, and standard error is in the standard error column, it's 0.000202. So the confidence interval is a matter of just taking the three pieces, plugging them in. So we get the following interval, 0.005 to 0.006. And so if we wanted to interpret that, what would we say? We are 95% confident that the interval from 0.0053 to 0.0061 captures the true slope of our regression line, right? So it's interpreted exactly the same as before. So we're 95% confident that our interval captures the slope of the true regression line relating flight timing or drop height. Okay? So that's our process there. Now, the other thing I would suggest you guys do, so here's your assignment, but I would definitely suggest that before you start the assignment, go through in your book and check out the two examples on 749 and page 754. They go a little bit more in depth into some of the processes involved with the testing and the confidence intervals. So you want to look at how much is that truck worth, look at what they solve, how they solve it, things like that. Also look at the crime versus IQ. And once you've gone through those examples, then try to do some of the problems there.
Will the following students please come to the front office? Caitlin
Yes.
Glazebrook, Mercy McMillan, Elliot Drift, Jonathan Greenfield, Brandon Boatwright. Please come to the front office.
What? No, I was gonna. It just bugs me. I'm glad I have more money. It's like enough to buy a whole drink. What? It's enough to buy a vitamin water almost. Well, then why don't you just spend that money? It'll be even. I can't do that on my checking account. I guess I can transfer the $139 to my checking account. Beach and activities, Skittles, whatever. We told me it's rich.
Yes. What's that? No.